The Krebs cycle. This is the third of the videos, so if you haven't seen the videos on glycolysis and link reaction, it might be worth you having a look at those particular videos now. So the Krebs cycle was named after a scientist, a German-British born scientist called Hans Krebs. It has nothing to do with bicycles. Instead, this time the cycle is what he's drawn behind him here. It is part of aerobic respiration. And you can see in the diagram behind it, started off with glucose, the respiratory substrate at the top. You can see the pyruvate. You can see the acetyl-CoA, so that's the link reaction with CO2 given off, decarboxylation. And you can see two hydrogens removed, the dehydrogenation. He doesn't show the coenzyme there that is carrying those hydrogens, the coenzyme that's being reduced, which if you've seen the previous videos, you should know is NAD. There's a few more steps beneath that, starting off with citrate, following all the way around to oxaloacetate. That's the Krebs cycle. A simple diagram, and I'm calling this a simple diagram of the Krebs cycle, is shown here. It's also called the citric acid cycle, so in some older textbooks you might find it called citric acid cycle. For OCR A2 biology, you do not need to know all these steps. That's the first point, so we're going to make this much simpler shortly. However, before you do that, just take time to look at all the things that come out of the cycle and go in. You can see at the top you've got acetyl-CoA. You should be familiar with that already from the link reaction. Going round clockwise, you can see there's decarboxylation, there's dehydrogenation, and then there's another step of decarboxylation and dehydrogenation. At the bottom of the cycle there, you can see there is substrate level phosphorylation with the production of ATP. Then there's more dehydrogenation. Here the coenzyme is different. It's FAD, flavin adenine dinucleotide, or flavin adenosine dinucleotide. And there's a final dehydrogenation at the top to go back to oxaloacetate. There's water input there, and there is actually water input in other parts of the cycle. We are going to ignore that. That is simply to make sure that there are enough hydrogen ions for the for the substrates here to be dehydrogenated. But we're going to ignore that for A2 OCR biology. So let's simplify this. So here's our cycle. We always begin with oxaloacetate. That is something you do need to remember, oxaloacetate. Although the chemical structure you do not need to know for A2 OCR biology. But I have put this on in this video simply for you to spot that it contains 4 carbons. So if anything, just please remember that oxaloacetate is 4 carbons. After the link reaction, which occurs inside the mitochondria, inside the matrix of the mitochondria, oxaloacetate combines with acetyl-CoA, which was produced in a link reaction. So these two molecules will combine, and the 2 carbons of acetyl-CoA and the 4 carbons of oxaloacetate make a 6-carbon compound called citrate. And for A2 OCR biology, you also need to remember that name, citrate. That's the only ones you need to remember: oxaloacetate, citrate, and acetyl-CoA. Now let's look at the main steps, what happens from then on. We get a decarboxylation. So once again, we get a carbon dioxide molecule produced. Don't forget, carbon dioxide is a product of aerobic respiration. We had 2 molecules produced in a link reaction. Now we've got a third. So we're looking for 3 more. We get a dehydrogenation reaction. So NAD comes into the cycle, and it oxidizes the structure of citrate. Well, it's not citrate at the time, and becomes reduced itself. So we get reduced NAD. It takes away a hydrogen atom. And because we've got decarboxylation, we've now moved from citrate to a 5-carbon compound. The name you do not need to know for OCR biology. The cycle continues. We get another decarboxylation. That now makes 4 carbon dioxides. We get further dehydrogenation. The coenzyme NAD is reduced to become reduced NAD. And because we had that decarboxylation, we no longer have a 5-carbon compound, we have a 4-carbon compound. The name is not important for OCR biology. The cycle continues. Now here we get an input of ADP, adenosine diphosphate, and a phosphate atom. And we get substrate level phosphorylation to produce a molecule of ATP. So now we have made ATP. We've input some energy to make ATP, this universal energy currency. FAD comes in now, the other coenzyme. It reduces the 4-carbon compound to make reduced FAD. So it's another dehydrogenation. And we get our final dehydrogenation, reduction of NAD to make reduced NAD. Now once they have been produced, there's no decarboxylation here, but the 4-carbon compound that has just been reduced by FAD and NAD and substrate level phosphorylation undergoes a chemical change with an isomerase enzyme, so it changes the chemical structure, and we're back to oxaloacetate, which is the beginning of our Krebs cycle again. If you want to relook at this again, to do so, it will help you to understand the stages going on. So you just need to remember what's in the Krebs cycle in terms of oxaloacetate, acetyl-CoA coming in, and citrate, but remember the output. Look at the carbon dioxide, decarboxylation. Look at the reduced NAD and FAD, dehydrogenation, and look at the ATP. So keywords for this particular section: decarboxylation, dehydrogenation, substrate level phosphorylation, and of course the compounds in the Krebs cycle and what enters the Krebs cycle that you need to remember. Now, remember we are talking about respiration of glucose. Glucose in glycolysis produce 2 molecules of pyruvate, therefore 2 molecules of pyruvate underwent the link reaction to make 2 molecules of acetyl-CoA. Therefore, per glucose molecule, this Krebs cycle is going to happen twice, 2 turns of the cycle. We will therefore get 4 molecules of carbon dioxide plus the 2 from link reaction now makes 6 molecules of carbon dioxide per glucose molecule. That's the respiration equation finished there. We've got a total of 6 molecules of reduced NAD. Remember we had 2 from the link reaction as well and 2 from glycolysis. You might want to work out how many that's in total now for the next stage of respiration. 2 molecules of reduced FAD. Although I spoke to reduced there, I do mean reduced. And 2 molecules of ATP. Remember the 2 molecules of ATP produced in glycolysis as well? So that's now 4 in total from 1 molecule of glucose. But please bear in mind respiration is not finished yet. We still have to go to the final stage after the Krebs cycle. Right, so there's the Krebs cycle picture I put on before. Now hopefully it doesn't look overcomplicated now. You should be able to spot the compounds you don't need to remember, such as isocitric acid all the way down to malate. But just please remember that we go from a 6-carbon compound all the way around to a 5, and then all the way around to a 4-carbon compound, which is called oxaloacetate. You can see the decarboxylation, you can see the reduction, you can see the substrate level phosphorylation.